Hello everybody and welcome back to the continuation of example 1. In the previous video we did the calculations in parts A and B of this problem, and in this video we're going to complete it and do the calculations in parts C and D here. Okay, so let's start by recalling kind of what this problem was all about. So we were talking about two particular permutations in S4, alpha and beta. We wrote those in cycle notation. We're going to continue to use those cycle representations. And so in part C, they'd like us to calculate beta cubed. And remember what the operation in our group here is. It's function composition. Okay, so beta cubed really represents repeated composition of the permutation beta with itself. We can maybe start by calculating beta squared, which is just the composition of beta with itself. Okay, we're interested in what permutation we get if we do that. So as is customary here, we're going to start with the number 1 and ask, where does that get mapped to? Okay, well, we start with the second copy of beta. We see that that maps 1 to 2, okay, and then 2 gets mapped to 4. So the net result is that we started with 1 and we ended up with 4, so the next number in our cycle over here is going to be 4. All right, and then the question is, where does 4 go? Well, if we start here, 4 wraps around and maps to 1, and then 1 gets mapped to 2. So net result is that 4 goes to 2, and so 2 is the next number in our cycle. Okay, and then where does 2 go? Okay, well, let's see. 2 is going to go to 4, and then 4 wraps around and hits 1, so 2 is going to end up hitting 1. That tells us that we need to close this cycle. Okay, so we've just calculated beta squared in our group. Okay, how would we calculate beta cubed then? Well, basically, we just need to take the beta squared that we already calculated and compose it with beta. So we'll start by writing beta squared. That was the result of our last calculation. Compose that with beta. And now we're interested in just seeing what we get here. All right, so we'll start with the number 1. And let's see. So 1 is going to map to 2, and then 2 wraps around and maps back to 1. So kind of interesting. We started at 1 and we ended at 1, so this cycle closes. 1 just maps to itself. Okay, and we've got several other numbers to talk about. Okay, 2, 3, and 4, so let's just pick one of them. Okay, so where does 2 go? Well, let's see. 2 maps to 4, and 4 maps to 2. Oh, we started at 2 and we ended at 2, so that cycle also closes. Okay, what about 3? Okay, well, 3 doesn't appear in any of those, in either of these cycles that we have here, so 3 maps to itself, and you can check that 4 would map to itself as well. So every single number maps to itself in this permutation. What we are really looking at is the identity permutation. Every number gets mapped to itself. So we have just found the identity element in this group S4. Okay, now I want to remind you of one comment that we made in a previous video here. We talked about how generally, if a number maps to itself, you don't write it. But it's kind of weird in our case because every number maps to itself. And so if we omitted all 4 of those numbers, we'd have a blank space in front of us. We'd write nothing. And that would be kind of weird. We don't want to do that. So generally what you do if everything maps to itself is you just pick one number, usually 1, and just write that. Okay? That communicates the fact that 1 maps to itself, and the absence of the other 3 numbers, 2, 3, and 4, tell us that those 3 numbers also map to themselves. Okay? So there's the identity permutation. That's the result of our calculation. Okay, one other comment just on notation here. There is a second kind of generic way of writing down the identity permutation. I want to make you aware of that. Okay, we can also write epsilon, okay, to denote the identity permutation. Okay, that's just a notation that somebody chose. So when you see epsilon in the context of our course, that's just another way of representing this identity permutation, kind of generically, in any symmetric group. Okay, so we have completed the calculation for C. What about D? Okay, so D is asking us to actually calculate the cyclic subgroup generated by an element alpha. We've done this calculation in other groups. This is the first time that we've done it in a symmetric group. Okay, what does that mean again? Okay, well, this notation represents just the set of all powers of the element alpha. Okay, so we'll start with what alpha is equal to. So that's the permutation 1, 2, 3, 4. Okay, we just need to calculate powers of that. And what we're going to observe is that if we raise this to a high enough power, we're going to come back to the identity, just the way that generally happens in any finite group. Okay, so alpha squared then would be just taking this permutation and composing it together. Okay, and so let's see. If we start with the number 1, 1 is going to go to 2, and 2 is going to go to 3, so 1 goes to 3. Okay, and then where does 3 go? Well, 3 maps to 4, 4 maps back to 1. So 3 goes back to 1, which tells us that we need to close that cycle. Okay, and so we've taken care of the numbers 1 and 3. What about 2 and 4? Let's pick one of them, 2, and ask where does it get mapped? Okay, well, let's see. So 2 is going to get mapped to 3, 3 is going to get mapped to 4, so 2 goes to 4. And then 4 maps to 1, and 1 maps to 2, so 4 goes back to 2. We're going to close this cycle. And what we have here, that's the result of the calculation alpha squared. All right. So far, we've got 2 elements, okay, in this subgroup that we're generating. Let's look at the next power. So alpha cubed, we would get alpha cubed by taking alpha squared, which we just calculated. Let's write that down. 1, 3, 2, 4. Okay, and composing that with alpha again. Okay, and seeing what we get. So let's see, if we start with the number 1, 1 maps to 2, 2 maps to 4, and then 4 stays the same here. So we started with 1 and ended up at 4. Okay. And let's see, 4 maps to 1, stays the same here, and then 1 maps to 3. So we started at 4 and ended up at 3. Okay, and then 3, let's see, that maps to 4, stays the same. Oh, sorry, no, it doesn't. Back up a minute. So 3 went to 4, 4 maps to 2, and then it stays the same. So we started at 3 and ended up at 2, and then finally, where does 2 go? All right, so 2 goes to 3, 3 stays the same, and then 3 goes back to 1. So we can see that we started at 2 and ended up at 1. We're going to close our cycle. All right, so there's alpha cubed. We're still not back to the identity, so we've still got a little bit more work to do here. So what is alpha to the 4th? Okay, well, that's going to be alpha cubed. Okay, so the result of our last calculation times alpha one more time. Okay, what happens there? Okay, well, if we start with 1, 1 goes to 2, and 2 goes back to 1, so 1 goes to itself. And what you're going to notice is that all of the other numbers go to themselves as well. Let's just check one more together. So if we ask where does 2 go, 2 goes to 3, and 3 goes back to 2. So 2 maps to itself, so I'm not going to bother to write that. 3 goes to 4, and 4 goes to 3, so 3 maps to itself. And I'll leave it to you to confirm that 4 also maps to itself. All right, and so the result of this calculation is the identity we have wrapped around, and the upshot of it is that the cyclic subgroup is going to contain 4 elements in it. Okay, the 4 elements that we just calculated. All right, so our conclusion is the following here. Okay, let's write out the elements. So we got the identity, 1, 2, 3, 4, 1, 3, 2, 4. and 1, 4, 3, 2. Now notice, it doesn't matter the order that we write these in. Okay, order is irrelevant because we're talking about a set here. Okay, there's the cyclic subgroup generated by the element alpha. Okay, we've completed the calculations here, but I would like to add one comment to this. Okay, notice that in part C, we started with the cycle 1, 2, 4, and we noticed that when we raised it to the third power, we got the identity. So it had order 3 in this group. Okay, and then in part D, we started with a cycle of order, or a cycle with 4 elements in it, and we raised it to the fourth power and got the identity, so it had order 4. And so what we've kind of discovered is a general fact here, and that is that if you take a permutation that has a cycle with n elements in it, its order is always going to be n. That's an observation that's worth writing down. So the order of a cycle of length n is always n. And that's an observation that might help just with calculations that you do. All right, and we're done with example 1.